Kinetic and molecular theory, effusion, diffusion, real gases. When we talk the kinetic molecular theory, the point you want to remember is that kinetic molecular theory is all about why. It's all about why changing pressure affects the volume, why changing the temperature affects the pressure, all of the ways the physical properties of a gas interact. And the kinetic molecular theory explains this. Now, what the kinetic molecular theory does is it has 5 postulates, which we're going to review again, and it's explaining pressure and temperature and how those two interact. Now, the first point is the continuous random motion of particles. So when we talk about the why, there are certain assumptions that we make. This is the first one. The second one is that the combined volume of all the gases is small compared to the relative volume. In other words, I have a gas occupying space, and the space between the particles, the volume container in essence, if I put all of those dots together into one spot, their volume compared to the volume they occupy is very different. In essence, when we talk about this, they can be, a gas in essence is compressible. So if I can compress a gas, that means there's a lot of empty space that I can force the particles to occupy less and less space because I'm eliminating the space between the particles. So that's what this is talking about. The next one talks about the attractive and repulsive forces, or the lack thereof. What we observe within a container is we know that the particles are constantly bouncing off each other, off the container or the walls. So we have these collisions, but the attractions between the particles are negligible. The importance of this is even when particles bounce off each other, my momentum is conserved. I may transfer kinetic energy, so I may have a slow particle that gets hit by a really fast particle, and so when they collide, this one may now move fast and this one may move slower, but the collision was elastic in that the momentum was conserved. Now, the other thing to keep in mind is the point being, if there are no intermolecular forces, no attractive and repulsive forces between the gas molecules, then gases will always behave ideally. And that's ultimately the point of the kinetic molecular theory, is that all gases are ideal gases. So we'll be talking about why they're not, but this is the thing to keep in mind, is that the kinetic molecular theory treats all gases as ideal. Now, first thing we're going to talk about with it has to do with this, it's sort of like one of the Maxwell-Boltzmann graphs. In essence, what you're looking at is we are seeing how molecules and their speeds can vary within a sample. The point, when we talk about the kinetic molecular theory, what we're saying is that the particles have an average kinetic energy. This graph is showing you the average kinetic energy. In other words, I have particles going from 0 to 10 to the second. Now, the point here is what the graph is showing me. So when we go to define each of these areas, the u is my velocity. So in this case, my u equals my velocity. And we have 3 velocities to look at. We have what's known as the most probable, the average, and the root mean square. Okay, so when we look at this and we look at the average kinetic energy, the lower the temperature, so this first one is 0 degrees and the next one is 100 degrees. The main thing to notice is, see how the fraction of molecules changes? The fraction changes with temperature. And by that, I mean, when you look at this bigger one, there's more particles at various speeds in the larger temperature. The higher the temperature, the more varied the kinetic energy. The lower the temperature, the less varied the temperature, the less varied the kinetic energy of the individual particles. So that's really what we're looking at when we see something like this. Now, you see this a couple of different ways, but the primary thing is when you look at a variety of samples at a variety of temperatures, you see the plane, this graph, start to flatten out and extend out even further. And so we always have, at higher temperatures, you're always going to have a shift and an increase in the range of temperatures. That's basically the point. Where we see the effects of the various speeds of the particles is in effusion. And in essence, basic definition, effusion, a gas escapes through a pinhole. We have a pinhole link. Where this becomes obvious is when you look at balloons. We all know helium balloons float. Helium is less dense than air, but helium also eventually will lose the helium inside, and so because it loses the helium inside, it begins becoming less dense because the helium goes away. The reason is because of the rate of effusion. Okay, the rate of effusion is important because it's based off that idea that we talked about today in terms of kinetic energy. So I have kinetic energy that determines, that is based on mass and velocity. So when I look at my kinetic energies for two different, when I look at my kinetic energy for two different gases, if they're at the same temperature, the kinetic energy is the same. So same temperature, the kinetic energy will be the same. If the kinetic energy is the same and they're different masses, by definition, the volume has to be different. So we get this relationship. In other words, what we see is we see an inverse relationship. The higher the mass of the particle, the lower the velocity of the particle. So when we look at effusion and we talk about the rate of effusion, the lighter the gas, the faster it will effuse. Let me get rid of that. So the heavier the gas, the slower it effuses. So when you look at the argon and the helium balloons, the argon is naturally more dense than air, which is 78% nitrogen and about 20% oxygen, 18% oxygen, thereabouts. You see this difference. So the helium balloon ends up sinking faster than the argon balloon rises because of this difference in the mass and the velocity. Now, this also impacts diffusion. But diffusion, there's a lot more going on with diffusion because diffusion has a lot to do with this idea of distance traveled in a single movement. So you start at one place, it moves to another, it bounces off molecules and existing particles, it bounces off containers, and so you have this very complex movement that they've tried to demonstrate with the yellow. And so diffusion is much more complex than effusion, but it's also based on the same idea that mass and velocity are inversely related. And that's really the point. When we talk about gases and we talk about their behavior, it ultimately boils down to that. Now, real gases, okay, don't behave ideally. And when they don't behave ideally is when we have high temperature and low pressure. So they won't behave ideally under those conditions. And this sort of makes sense. So when we look at the real gases, we start seeing very non-ideal behavior because, and it goes back to the tenets of the kinetic theory. Again, the first one, that volume is negligible. If volume is negligible, so here's the deal. At high pressure and low temperature, all of our assumptions eliminate. In other words, we can't compress a gas to infinity. The particles that what we assume is the negligible volume is no longer true because if we get them pushed close enough together, the particle volume does become important. And so we have to eventually correct for that. The other thing is that there's no attractive forces between the gas molecules. The reason this becomes an issue is we know that they change phase. I can turn a gas into a solid, I can turn a gas into a liquid. And so because of that, we know that there are interactions between the particles. We know that there are attractions and repulsions between the particles. And this breaks down, and so in essence, according to the kinetic molecular theory, the tenets of it, no gas would ever change state. Real gases do change state, and they change state at high pressure and low temperatures. Now, we can correct for this, and this is what's known as the van der Waals equation. Now, if you ever have to do the van der Waals equation, you're always going to be given your A's, and you're always going to be given your B's. So you're going to be given A, you're going to be given B, and typically you're even provided the equation. The main point to recognize with the equation is what it's correcting for. The van der Waals equation is correcting for the deviations from ideal behavior. It's correcting for the volume, and it's correcting for the attractive forces. That's what our A and our B represent. So B, liters per mole, that's going to be dealing with the actual volume the molecules occupy. The A, the liter atmospheres per mole squared, that's going to be correcting for the attractions between the molecules.